Okay, our last speaker before the break is Oliver Schmitz, and he'll be also talking about LC LC.
First of all, I want to say thank you to the organizer of this very nice conference. You have done a great job. Thank you very much. And in the next 20 minutes, I will show you the development of a new analytical platform based on several works of PhD students and postdocs. And the work was or is done in my labs at the University of Duisburg-Essen, and these are the members of my group. And in the next slides, you will see sometimes some pictures of these guys, and these are the heroes. They have done the work. I'm only a presenter and a money maker, but the work comes from these guys, okay? So, and the analytical platform we have developed should be used for complex samples, okay? And complex samples are, for example, sorry, I will find the wrong way, so this one now. I learn it, okay. So, for example, tumor samples or algae banks, blood, wastewater, urine, air pollution, food, raw oil, or shiny soaps. And I know we all like separation, me too, but the main goal should be the identification of the compounds and not only the separation. And that means we have to think about identification levels. And in my lab, we use the identification levels from Emma Szymanski. They defined 5 levels, and the lowest level is mass of interest. So this is very easy. Level 4 is also easy because you only need money. With an Orbitrap, it is fine, you get the sum formula. Level 3 is also possible with Orbitrap if the abundance of the signal is high enough so that you can do MS-MS. Level 2, you need luck because you have to find the MS-MS spectra in the literature, and then you have to synthesize or buy the reference standard and confirm it via retention time, for example. How can we reach these levels? Well, in my lab, we use this workflow for non-target analysis, and you see we have a lot of software, MS-DIAL, Skyline, Medline, MS Cloud, MedFrag, and so on. But at the end of the day, we have to conform the signals with a standard. And to find the right standard, we need an idea which standard it is, which isomer it is, for example. And for this, we have to separate the isomers also. So that means we need a good separation. And everybody knows this equation here, I think, and this wonderful scheme from Petzendra. And you can see here that retention factor plays not a big role. You have 2 other parameters. This is the selectivity, which has the best influence, and then we have the efficiency term. But the problem in the efficiency is that you have here the square root. But we can do it very easily. We can increase the length of our HPLC column, and when we do it, for example, these isomers cannot be separated very well with a 250 millimeter column, but if we use 4 columns, so that means we have a 1 meter stationary phase, we can separate it and the equation works. We have a doubling of the retention of the separation power by 4-fold length increase, but you see also the signals are broad, and therefore the limit of detection, the signal to noise level is bad. And of course, the analysis time is increased dramatically. After the nice talk from Dwight, it's not necessary to explain the LC LC, but with comprehensive 2-dimensional LC, we have a wonderful possibility to increase the selectivity of this separation. And here you see a counterplot of an LC LC run from a drug, and also fly over a GC chromatogram. This is from Jens Dalek. Okay, the method optimization in GC is not very complicated in comparison to LC LC. In LC LC, you need very strong experience in chromatography. And here we started a cooperation with Tao Yuan from the University of British Columbia. He has developed an algorithm, and this algorithm tries to separate 100 or more most abundant features as best as possible. And we now at the moment try to use this algorithm for the method optimization in LC times LC. And we have several columns, and we check it at the moment. So here you see, for example, for PFP in the first dimension, we start with a more or less linear gradient, and this is the result, and then the software tells us what we should change. And so step by step, we come to a better separation index, and here you see this is the best one, and after that it goes down. Of course, you don't see that this is better as here, because these are DAD, and the software works with MS data, but I cannot show you the MS data, it makes no sense. So, and we do this also for other columns, and in the near future we will compare it with our homemade gradient, and then I will tell you if it works or not. This is an ongoing process. The next problem we have in LC-LC is, for example, that if you have a complex sample, and this one is a liquor, you see when we use PFP in the first and helix in the second dimension, it works at the beginning very nice, because at the beginning very polar compounds elude out of the PFP phase, and then helix works fantastic. But later, when the analytes are non-polar, you have a problem with helix, there is no separation. If you have a C18 in the second dimension, then you have at the end of the run in the first dimension very nice separation, but at the beginning for the polar compounds, C18 has no retention. So this is a problem, and what we need is a combination of both. And to realize this, we have added further valve where we can switch between two different stationary phases in the second dimension. We are in the beginning, we have the flow, the loops, the content of the loops go to the helix, and later to the C18. And for better focusing on the columns in the second dimension, we can here add at the beginning acetonitrile and later water, so we have a focusing effect. This works very well. These are the two chromatograms with different stationary phases in the second dimension, and this is the combination of both, and you see it works. So, and we use this technique for a lot of samples in my lab, for example, also for the extract of such a herb. And we compare it with classical LC times LC, and you see with the MULTI-2D LC, the separation is better. Next problem we have in LC LC is often, from a practical view, you have the contour plot, and you can only look for one wavelength, and so you have to scroll through the wavelength. And Jacqueline has written a very small program so that we can generate a movie where we can see which wavelength, the whole chromatogram on different wavelengths. So the separation is nice, but of course with a DAD you cannot do anything as a complex sample. So we need an MS, but which ion source? If the compounds are very polar, that means it comes from a helix, electrospray is the best. For non-polar compounds, maybe APCI or another ion source is better. And therefore we have developed a dual ion source, where the eluate from the helix goes ionized with electrospray, and the others with TPI, tube plasma ionization. APCI is not possible because we use an Agilent MS, and an Agilent MS has the voltage on the MS capillary, and the ground is on the ESI emitter or at the corona needle. And if you have both in the same dual source, you cannot work. So this is the problem with Agilent and Bruker. For other MS, we can do this. So therefore, we use TPI. And very short what TPI is. We have developed it in our lab. We have a high voltage applied on a needle, and the needle is in the dielectric tube. This is a quartz glass sample with an inner diameter of 0.6 millimeter. And with a T-piece, we have a discharge gas. In our case, normally we use argon. And then you get a plasma, because it is a dielectric barrier discharge. And with a vaporizer from an APCI probe, for example, the vaporized analytes come to the plasma and are ionized. We have developed a lot of such dielectric barrier discharge in my lab. Inverse low temperature plasma, tube plasma, micro tube plasma, and also this new one. But we use at the moment this at the most. It's the best ion source in our lab. And we do it in coupling for LC and also for GC. That means we have the same ion source, and after a little bit construction, we can add an LC or a GC to the same atmospheric pressure QTOF or triple quad or what else. So and it works very well. We use it a lot of. You can see it here. It works nice. And now we come to the dual source. The construction is very simple. We make an ion source where we can add the electrospray in this way and the TPI in front of them, and with the sliding hinges we can optimize the position of the plasma in the ion source. The big problem was not the construction, the problem was the connection to the MS. I will show you this later. Here you see first how it looks like here, and if you open the source, you see here the Agilent jet stream electrospray, the vaporizer, and here our LTP ion source. So the connection was a problem, but with the help of Agilent in Santa Clara, we could realize that the MS knows that we need an ESI and also APCI vaporizer at the same time. And then we have checked it with a lot of standards, and you see here the original ESI from Agilent, the dual source ESI, a little bit not the results of the original, a little bit better because we make a small mistake, so the position is not the same. And here you see the TPI, and every green marked numbers are the best. And you see for some cases the TPI is better as the ESI and vice versa. So it makes sense to combine both. And here's the very first result, extract of this plant. This is the whole analysis with the Agilent source. The whole analysis with TPI, and here we switched between ESI and TPI. This is a bad result because you see it works, but to be honest, ESI in total would be better. So this is a bad example. We are looking now for a better sample to show you the benefit. So separation and detection is fine. What is with identification? This is a Hediotis diffuser extraction, and we are interested in this compound. And DAD is not helpful, but we have an MS, a TOF, and with a TOF you have no chance for the sum formula. You need an orbit trap for this. But we get, in this case, 7 different possible sum formulas, but you see the score. 5 scores are higher as 99%, so one of this will be the right one, maybe. And we are lucky because this sum formula could be routine, and routine is a compound which is very often found in plants. And so we have QTOFs, that means we can make MS, and we found this fragment, and it could be routine because this part has this mass. We are level 3. Now we go in literature, and we are lucky. We found an MS spectra of routine, and yes, it has the same fragment, so level 2 we reach, and then we board routine and compare the retention time, and so we come to level 1. But this was luck, so it is not a normal way. So now we have the same situation as NASA. We have nice separation. Also with Hubble we see a lot of, but we have no idea about the identification. And here we have also not enough information. NASA has a lot of money, and they built the James Webb Space Telescope, but what can we do? So, and maybe mobility is the idea, or could be help. So when we analyze with LC LC extract of these 2 plants, this is very often used in China in the cancer therapy. We have a wonderful separation. The contrast is not good, but the separation is one of our best separation. So unfortunately, the separation time was 180 minutes. When we now use a one-dimensional LC and couple it with drift tube mobility, we have also a wonderful separation for the same sample. but only in 22 minutes. So this is great, and it's much easier because one-dimensional LC is simple to optimize. And now we have a lot of happiness in my lab because since 1 month we have the next generation iMobility, and this is based on a printed circuit board so that you have a 13-meter path length for separation. This leads to a 200 resolving power, so peak capacity. This is wonderful. And these are the first results from yesterday. We have analyzed a lipidome analysis with 1D LC, and here you see the separation. This is great, much better as with the drift tube iMobility. So this is very promising. And for identification, the drift tube or the iMobility is good because we have an increasing database of CCS values. And you see here from Aaron Baker, wonderful work, 28,000 standard at the moment. And if this base is increased, then we have a nice tool for identification. But 1D LC and 2D LC, there's one major drawback in 1D LC, and this is the ion suppression. We have spiked these two compounds in 3 different matrices, in a plant extract, wastewater, and biocoal. And here you see the ion suppression. One would mean we have no ion suppression. That means in 1D LC, we have 40% ion suppression, and here 80%. With 2D LC, we have, for these two samples, a nice, very low ion suppression, but for biocoal also 50%. You see there's a big advantage of LC times LC because it reduces the ion suppression, especially with electrospray ionization. And therefore, we want to combine both, the best of 2 worlds, beer and wine, but maybe you have checked it yesterday, sometimes you get a headache. And the reason for this is that we have now 4 dimensions of data processing. One retention time in the first dimension, then another one in the second dimension, the iMobility drift time, and the MZ value. And how could we display these 4 dimensions? Due to this reason, Jacqueline has developed a standalone program based on Python to reduce the dimension, and she called it peak selection and combined peak. And after the measurement, MS-DIAL is used for the peak finding and integration, and then the data frames are loaded in the program, and anything works from alone. That means we have the analyze, we have the MS-DIAL, and then we make a clustering. We make a clustering of MZ, M over Z, and also the clustering about the time in consideration with the modulation time. And then we add the areas of one cluster to the peak with the highest abundance. And that means we have from 3 compounds, 3 clusters, we get 3 signals. I know that the retention time is not the best to do this in this way, but it works, and we have no other idea. So here you see a real sample, Underberg. This is a German liquor. I don't like this because the taste is not nice, but the sample is great because it's based on 27 herb extracts, so very, very complex, and therefore we like it very much. So, and we start with this, and if you look the M over Z cluster with MZ 150.092, you have a lot of features. And with our declustering, we see that we can separate from all of these features 5 clusters. And also clusters 3 and 4 was not a problem because the time range is the same, but there's different in the modulation, so we can work with this. Also here, another M over Z clustering, it works very nice. And in the next step, we use the drift tube also in this. That means we make LC LC-ESI mobility MS. And here, for first check, we use these 2 compounds. They cannot be separated in LC times LC, and of course also not in MS, but they have different CCS values, and our program finds these and give us 2 signals for these compounds. And in the next step, we go back to the Underberg, also with drift tube eye mobility. You see this as a heat map, very complex. And at the moment, Jacqueline goes in very in detail in the raw data and look if this program makes mistakes or not. And if there are mistakes, she will change the clustering program. And after that, we will publish it. So this is what I want to show you today. And here's a summary. I show you the multi-2D LC, the algorithms for the optimization of the gradients, the TPI dual source, then this useful small tool for data analysis, the new clustering system, and the mobile ion, and the outlook. And thank you to my group and the companies and organization for money, and you for your attention. Thank you.